Good day, everyone, and welcome to our elementary theory of number class. So our topic for today is all about the least common multiple, and I am Joyce Legaspi, your discussant for today. So before we start, let us have an objectives. At the end of this lesson, the student should be able to first is to illustrate canonical decomposition and its example. Second is to determine the number of trailing zeros in n factorial. And lastly is to find the least common multiple or LCM using prime factorization. So what is canonical decomposition? The canonical decomposition of a positive integer n is of the form n is equal to p sub 1 raised to a sub 1 times p sub 2 raised to a sub 2 up to p sub k raised to a sub k, where p sub 1 and p sub 2 up to p sub k are distinct primes with p sub 1 is less than p sub 2 less than up to less than p sub r. And each exponent a sub I up to a sub k is a positive integer. In short, the primes occur in increasing order or in numerical order. For us to really understand, let us have an example. So for direction, find the canonical decomposition of the given examples. So for example, number 1, we have 2,520. So to find the canonical decomposition of this example, we are going to use the continuous division. So we see that 2,520 is divisible by 2 and 2 is the smallest prime number. Therefore, 2,520 can divide by 2. So if we divide 2,520 by 2, the answer is 1,260. So continue the process as 1,260 is divisible by 2. So 1,260 divides by 2, the answer is 630. And 630 divides by 2, the answer is 315. So we are not finished yet because 315 is not prime. However, we know that 315 is divisible by 5. So we can divide 315 to 5. The answer is 63. Okay? And 63 divides by 3, the answer is 21. And 21 divides by 3 is 7. Then 7 divides by 7, the answer is 1. And for this example, the canonical decomposition here is 2 cubed times 3 squared times 5 times 7. And as you notice, our canonical decomposition is um, in numerical order or in increasing order. Next is 1,863. So we are going to use again the continuous division to find the canonical decomposition of 1,863. So we see that 1,863 is divisible by 3. So we can divide 1,863 by 3. So the answer is 621. Continue the process. 621 divides by 3, the answer is 207. And 207 divides by 3, the answer is 69. So 69 is divisible also by 3. Therefore, 69 divides by 3, the answer is 23. And 23 divides by 23 is equal to 1 since 23 is a prime numbers. So the canonical decomposition of 1,863 or 3 raised to 4 times 23. And it is in numerical or in increasing order. Next, let's move on to the trailing zeros in n factorial. By the number of trailing zeros in n factorial, by the fundamental theorem of arithmetic, n factorial can be factored as 2 raised to 8 times 5 raised to b times C, where A and B are positive integers and C denotes the product of primes other than 2 and 5. And for the formula, we always remember that E is the number of products of the form 2 times 5 in a prime factorization of n factorial. And it is the minimum of A and B. So if the number or the n factorial is higher, we can use the alternative formula, which is the highest power E of a prime P is equal to 5 that divides n factorial is given by E, or the power of E is equal to the floor function of n over P plus the floor function of n over P squared plus n plus the floor function of n over P cubed plus up to. So let k be the smallest integer such that p raised to k is greater than n, and n divides by p raised to k is equal to 0. So the sum is a finite one. Okay? So for us to really understand, let us have an example. So find the number of trailing zeros in the following examples. Let's have an example number 1, which is 120 factorial. Since 120 factorial is a largest number, or is a large number rather, so we can use the alternative formula of trailing zeros, or to find the number of trailing zeros. So we can use the formula of alternative in trailing zeros. So we have now the E, or the power of E, is equal to the floor function of n over p plus the floor function of n over p squared plus the floor function of n over p cubed plus up. Okay, so we can substitute the formula where n is 120 based on our example, and p is equal to 5, which is 5 is the highest power of prime based on the definition of the number of trailing zeros in n factorial. So we can substitute. So 120 is n, then p is equal to 5. Then next is 120 divides by 5 squared, and 120 divides by 5 cubed. So if we simplify this, we have now 120 divided 5 is 24, and 120 divides 5 squared, or 25, is 4, and 120 divides 5 cubed, or 125, is 0. So if we can sum up this, 24 plus 4 plus 0, the answer is 28. Therefore, there are 28 trailing zeros are there in 120 factorial. Next example is 561. So again, 561 is a large number, so we can use the alternative formula of the trailing zeros. So we have now the E is equal to the floor function of n over p plus the floor function of n over p squared plus the floor function of n over p cubed plus up to. So we can continue the process. So substitute the numbers to our formula. So n is 561, and 5 is the highest power of prime. So 561 divides by 5, and 561 divides by 5 squared, and 560 divides by 5 cubed. So simplify. 561 divides by 5, the answer is 112. 561 divides 25 is 22. And 560 divides by 5 cubed, or 125, is 4. So we add this 124, 112, 22, and 4. We come up to 138. So the trailing zeros are there in 561 factorial is 138. Finally, we are now in LCM, or least common multiple. So the least common multiple, or LCM, of two non-zero integers a and b is the least positive integer m, divisible by both a and b, and it is denoted by A and B, or the LCM of A and B. And for the formula of least common multiple, we have the LCM of A and B is equal to A times B over GCD of A and B. And the least common multiple has the basic properties. For letter A, or the first basic property, we have if LCM A and B is equal to M and M is equal to A is equal to B, then GCD of A and B is equal to 1. Letter B, if M is a common multiple of A and B and M is equal to A is equal to B, and B is the GCD of A and B is equal to 1, then M is equal to M. Letter C, if M is a common multiple of A and B, then M divides M. Letter D, if M divides A and N divides A, then the LCM of M and N is divides A. And for letter E, if N is an integer, then N times LCM of A and B is equal to the LCM of AN and BN. And lastly, if A is equal to P sub 1 raised to alpha sub 1 up to P sub K raised to alpha sub K, and B is equal to P sub 1 raised to beta sub 1 up to P sub K raised to beta sub K, and alpha sub I and beta sub I is greater than or equal to 0, then I is equal to 1, 2, up to K, then LCM of A and B is equal to P sub 1, maximum of alpha sub 1 and beta sub 1, up to the P sub K, the maximum of alpha sub K and beta sub K. So those are the basic properties of LCM. Okay, so in LCM, let's have an example. So using the canonical decomposition of prime factorization of the given numbers, find their LCM. So we already knew the process of canonical decomposition, so we are easy to find the LCM of the given examples. So for number 1, we are going to find the LCM of 50 and 60. So we can use the continuous division to find the LCM of the given example. So we see that 50 and 60 is divisible by 2, and 2 is the smallest prime number. Therefore, 50 can divide by 2 and 60 can divide by 2. So 50 divided by 2, the answer is 25, and 60 divided by 2, the answer is 30. And we see that 25 and 30 is divisible by 5, so we can divide 25 to 5 and 30 to 5. 25 divided by 5, the answer is 5, and 30 divided by 5, the answer is 6. Okay, so since there is a number which is composite, or we can divide, so 5 divided by 1 is 1, then bring down 6 since 5 or since 6 cannot divide by 5. Okay, since there is a composite number which is 6, so we can divide 2 by 6. So bring down 1, then 6 divides by 2, the answer is 3. Okay, and 3 divides by 3, the answer is 1. And for the LCM, we can arrange it in increasing order or in numerical order. So we have now 2 squared times 5 squared times 3. So if we simplify this, 2 squared times 5 squared times 3, the answer is 300. Therefore, the LCM of 50 and 60 is 300. Next is 16, 24, and 28. So we can see that 16, 24, and 28 are divisible in 2. So we can divide 2 by 16, 24, and 28. So 16 divides by 2, the answer is 8. 24 divides by 2, the answer is 12. And 28 divides by 2, the answer is 14. And it is also divisible by 2 again. So 8 divides by 2, the answer is 4. 12 divides by 2, the answer is 6. And 14 divides by 2 is 7. Okay, since it has two numbers that we can divide by 2. So continue the process. 4 divides by 2, the answer is 2. 6 divides by 2, the answer is 3. Okay, and 2 divides by 2, the answer is 1. And for the LCM, for 16, 24, and 28, we have 2 raised to 4, which is this, okay, and 3 times 7. Okay, so if we simplify this, we have 2 raised to 4 times 3 times 7. The answer is 336. So the LCM of 16, 24, and 28 is 336.